Okay. Okay, let's continue with the dirty paper coding basics. So yesterday we started by defining the optimum receiver alpha, which is the MMSC receiver. And then you can change the pointer here. So we define the optimum alpha just by minimizing the mean square error between the estimate and the actual transmitted message. First, ignoring the interference, existing interference vector S. And after a straightforward calculus, we got this alpha, which is P over P plus sigma squared. So you can actually see that this is, if you think about multi-antenna MMSC receiver, it has this form W, there's some interference here. HI. Okay. So it has a similar form, if you think. These are now vectors. If you make this H scalar, so we can write this as HP over HI squared TI plus N0, right? And if H is 1 or whatever, it has the same shape, right? So same form. So basically, it's a normalization by kind of SNR. So it takes into account the noise versus the power when normalizing the received signal. When the SNR is large, alpha becomes 1, right? Either this term becomes small or this term becomes large. So this the following works also with the alpha equals 1 case, but it's suboptimal. It's only asymptotically optimal when SNR goes to infinity. You can assume alpha is 1. But in general, you should use always the MMSC receiver. MMSC is information lossless, as we have noticed in the multi-antenna, the point-to-point multiplication. Okay. All right, let's assume now that this received signal, x1 plus SW, let's just rewrite it over here. Received signal is multiplied by the optimum receiver scalar. So all these terms are also multiplied with the same scalar. So we can obviously group some of these terms. This is the interference-free case, and this is the shift caused by the null.
Can you try with black?
Any better?
Yeah, a little bit better. Now, but
okay. Okay, so this is our equivalent model. So we have this alpha S that we should pre-compensate or pre-subtract at the transmit. All right. So the basic idea here, the basic principle of dirty paper coding is so-called extended constellation. So here we have a just very simplified scenario that we have this let's say this one here is like a QPSK constellation, right? So we have a 4 times extended QPSK constellation, right? So we can say without interference, this should be the origo, right? So we should basically be transmitting one of those 4 messages, right? Now we have extended the constellation such that it covers all possible shifts alpha S, right? So basically, the idea is that now when we have this interference vectors alpha S, it shifts the origo, right? So if the alpha S, if we want to send, for example, this symbol, right? But our and this is replicated 4 times. Okay. So if the alpha S happens to be, let's say, here, we find a point which is closest to this new origo, right? And then transmit this vector here. This would be the x1, right? And this is basically what we in the end what we are sending is a vector p, which is a vector sum of alpha S and x1, right? This is what happens here. Sorry, it's the difference. X1 is the difference between alpha S and the p vector, right? This is what we design. P vector is what we this is what we want to send to that given user, right? So generate P is basically sending the difference between the alpha S and P. So P obviously is a then sum of alpha S and x1. Okay, is that clear? Just basic vector math. So here we have alpha S plus x1 equals P, or P minus alpha S equals x1. On the other hand, if this alpha S happens to be pointing, for example, here, right, then the x1 would be this one. Okay.
So at the user side also this information is available. So
yeah, the user has to know this extended alphabet. Yes. It doesn't need to know the interference, but it has to know the extended alphabet.
Mm-hmm.
That's the complication.
Okay.
But on the other hand, if you think about our application, which is multi-antenna transmission broadcasting, right? So this S is also constrained by the same power constraints. This S could be another user that we are serving. So it's constrained by the same power constraint. So this S doesn't grow without limit, right? So the extended alphabet is not going to be extremely large, right? Compared to the single user case, because it's constrained by the same power constraint as, let's say, single user case. Okay.
Isn't it somehow loss of power? Because in order to transmit x1, we are transmitting P.
We are not you have to think that this is the sum power, right? We are transmitting this to one user and this to another user,
Okay.
right? Okay. Now, if we are allocating more users to this user, then this will be.
So the power will be the same?
Power is the same. The sum power is the same.
Even let's say the interference user is closer, even that case, the alpha S will be bigger, right?
But the sum will always be the same.
Alpha depends on the noise.
Yes.
Right, of course, then if alpha is small, it means that SNR is small as well. So the rate that we can send is also smaller, right? It scales. Okay, but anyways, let's see. If we now choose to send x1 to be now the difference between these two vectors. So what the receiver actually receives is this p vector, right? Because S1 S is already there, or alpha S is already there. Okay, so we can define this one now to be actually, given that p equals x1 plus alpha S, then alpha y, which is the output, the scaled output, we can declare to be the estimate of p hat, right? It's just x1 plus the noise, scaled noise. So this is the estimate of p. So now if we look at the difference between
I think can you try chunk?
by the way, this is permanent. All right.
Can you try blackboard? This whiteboard is reflecting light, so it's
Yeah. How come we have a permanent marker here? We don't have any other black.
no. Can you try this black?
Slightly more cumbersome though. All right. So now if we look at the, let's say, the mean square error between the estimate of P and the actual transmitted P, is this better?
Yes, it's much better.
Now we can start plugging in those expressions. Let's say P hat equals X hat MMS E plus alpha S. And then we have minus x1 plus alpha S. Okay. You can see that these two now cancel each other. It's equivalent as if the interference was not there. All right. Just simple. We are just moving the origo. Given the alpha S, we are moving the new origo over here, and then we're just speaking from the extended alphabet, the point that we want to communicate with the receiver. Of course, if you have this is very simplified scenario with, let's say, QPSK, but then like a Gaussian alphabet. This is like a projected to 2D now. You are just replicating all these points, and then alpha, if alpha is here and this is your desired point, you're sending this vector. If alpha is here, this is your desired point, you send this vector, and so forth, right?
How do we know the S before transmitting data to the receiver?
S is already given, right? So S is designed first without assuming anything. This is something that we will discuss later on. Now S is just fixed. Okay, S is also designed by the same transmitter. Or this can be in general. It could be also generated by another transmitter. But if that S is available at a transmitter, then it can be pre-subtracted, right? It's general. It applies in general, not only in our particular scenario. All right. So this is the basic idea of dirty paper coding. Dirty paper means that you have some dirt already on the paper, and then you design the new transmission given that dirty paper. That you're drawing something on top of the dirty paper, and it just want to make that already existing figure not to appear from the other user perspective or something like that. In fact, I mentioned that let me just have a in the book we have small detailed discussion about the importance of alpha. Does this show in the video?
No.
Well, you can go to the book, chapter 10, page 458, if you're interested. So here, in general, we can consider a domain of volume V. This is the volume V that covers all these extended or replicated alphabets. And we have an, so the K is the factor of the multiplicative factor of how many times we extend the alphabet or code book that covers n code words. And K is the replication. So we can have actually, in general, without this alpha, we can have these two conditions. And just like in the sphere packing interpretation that we covered yesterday for interference-free case, we can have these conditions that this number of these noise pairs, replicated noise pairs, is upper bounded by this volume, this arbitrary volume, which includes these K replicas, divided by the volume of the noise pair, right? So this is the total number of the symbols, K times n. And then we have this fair covering constraint that the number of the K should be larger than how did I say it? Basically, it should cover the number of times that we extend the alphabet should basically include the how could I say that this new origo is scaled by this X pair, right? I don't know how is it said in there. The spheres of grade is about to K replicas. So yeah, this is the constraint that these replicas should be able to cover all possible realizations of the interference with power P, right? So now you can actually come up with so this K actually cancels out. When you plug in these two constraints, you get a rate that is this half log SNR, right? So it misses this 1 plus term, right? So this is assuming alpha is 1, right? So this is the suboptimal strategy, because when the SNR is 1, the rate goes to 0, right? So, and it only starts to approach the AWGN capacity when SNR is really high. Okay. Okay, so here we have just another illustration of this process. What we do here is that we have the known interference vector S, right? And then we design the X1 given the scaled alpha S. So basically P vector would point to this point here. Then we add noise at the receiver, and we have the received signal. y, which is the summation of s plus x1 plus w, right? Interference, intended message, and the noise that we add at the receiver, right? And after scaling by alpha y equals alpha s plus the estimate, the interference-free estimate of the transmitted message, which includes the escape noise as well. Okay. As mentioned, this we need the receiver just needs to know the extended constellation. So it finds a point which is closest to p hat in the extended constellation, right? And that's it. So we discussed about the optimality of alpha, and the problem if alpha is 1 is that when we replicate, in principle, when you recall this the noise free case, I should be using the blackboard
Yeah,
only.
that is not visual.
Last time it was okay. Maybe it was
I guess it's because of daylight.
right. Okay, so we have this spare backing argument that we have a sphere. We could have this we could now define as x sphere, right? And the y sphere then is x sphere plus the noise. The y sphere, the receive signal includes also the impact of noise, right? So now if we think how these spheres, so the phi sphere would be actually larger than the x sphere because it includes the noise, right? Now if the noise is small, the x sphere and y sphere are almost the same, right? So we just want to count how many noise spheres we can fit into the y sphere, and that's fine. Okay, because now from the x, if we happen to get this point here, we just what did I say? Okay, if we want to replicate, right? If we want to replicate these y spheres, when noise becomes large with respect to the x sphere, then basically the phi sphere becomes much larger than the x sphere, right? Because it's mostly noise, right? So when we want to replicate these spheres, it makes sense first to scale by this alpha, because it scales y sphere to x sphere. Okay, let me go to these steps first, so it becomes clear how this scaling happens. It's actually this slide. So you recall that in the case when we had no interference, we just compared the volume of y sphere over volume of noise sphere. It's expressed in bits, and we get this log, half log 1 plus SNR, right? And that's okay when we are not when we don't have any interference. that so-called nearest nearest symbol decoding approach, assuming alpha equals 1. So now if we use alpha at the receiver, we scale both the noise sphere and Y sphere with alpha. Okay, so let's see what happens with the Y sphere when we scale Y sphere with alpha, right? We plug in here alpha times n times p plus n times sigma square. So we plug in the optimum alpha, which is P, it's of n goes here, P over P plus sigma square times n P plus n sigma square. So we have NP, which is the X sphere, right? So it scales Y sphere to X sphere. So now it doesn't depend on the noise. Similarly, when we scale the noise sphere with alpha, it becomes that expression over there, right? So now when we plug in the scaled Y sphere divided by scaled noise sphere, we get exactly the same expression, right? Scaling by the MMSC is information lossless, right? So for the single user case, it doesn't matter. This scaling doesn't matter. But for the for this interference case, when we want to replicate this these alphabets or constellations, we want to replicate these X spheres, right? Because if we replicate Y spheres, the noise actually extends. So the lower the SNR, the larger the Y sphere with respect to the X sphere, right? So we start losing. And that actually was shown in the rate expression that asymptotically we get just log 2 of SNR, right? But after scaling by alpha, we take the noise into account. We reduce the Y sphere to X sphere. Basically, we reduce also the noise sphere, right? Also in the book, there's an example about this noise sphere scaling, figure 10.22. Uncertainty region. Like now, the noise is large with respect to X, right? But after scaling by this optimum alpha, the noise sphere is reduced, while the X sphere, of course, is the same. So by using this optimum alpha, that's the most efficient way. So we can basically replicate these X spheres. That's the most efficient way of replicating these constellations. Also illustrated here. In the case without interference, if this is the X sphere, right, the noise sphere can be outside the X sphere, right? And when we use the nearest symbol decoding, there's no problem, right? We are not interfering anything else, right? But when we are replicating, right? If you are not scaling the noise sphere by Y, if you're using alpha, then we start to have error between these replicas, right? So the scaling is mandatory for optimality in case of, so that we can pack these X pairs as close to each other as possible, right? Right. Another illustration that, okay, when you have this alpha S, this is the original origin, the new origin is here. And this is the X pair around the new origin, right? So basically, for any possible, the number of replicas that we need to generate basically depends on the largest realization of alpha S to all directions, right? It's more or less clear. I just want to give you an intuition, right? This is actually, so how I just want to give an intuition how this idea of dirty paper coding can be now used in this multi-antenna downlink transmission, right? That you assume that you have already generated a message, then given that the user has this extended alphabet available, shifting the origo to the new point given by the existing interference and picking the vector pointing to that desired symbol in the extended alphabet gives that receiver as if there was no interference, right? Of course, this is not practical, and there have been some well, at least in the, let's say, after this capacity region and the dirty paper coding optimality for broadcast channel was discovered, there was a lot of research on how to design practical codes. And there has been some research which is not covered in this course. It's not so interesting in practice because, especially in the multi-antenna scenario, as you will notice later on in slide 5, if you use simple linear beamforming design, the extra gain that you would consider from this type of complicated dirty paper coding based design is quite small, right? The more important is to use this spatial degrees of freedom, and the extra gain is just a fraction, right? Especially the highest amount. This is something that we will discuss a bit more in the later phases. Okay. Now, downlink precoding with dirty paper coding. Let's again take this simple example that we already covered for the superposition coding. Okay, single antenna, 2 users. Let's assume that let's first assume that, okay, user 1 is closer, right? Closer to the base test. So, if you look at the receipt signal at user 1, that's H1. So we generate the message X, which is X1 plus X2, and obviously the time index is here as well. All right. So transmitted signal X is a superposition of the message intended to user 1 and message intended to user 2. Okay. So the user 1 receives H1 X1 plus H1 x2 plus noise at user 1. Okay. Now, if we could now assume that the user 2 let's see. The user 2 is now already generated, right? Without knowing x1, okay? So we can actually call this s, right? So this is now equivalent to the model that we already used, right? So from the user 1 perspective, using the dirty paper coding, this S is just the new origo, right? And given the power allocation, so now we have x1 follows complex Gaussian, x1 follows complex Gaussian, zero mean variance P1, x2 complex Gaussian, zero mean P2. So given that we can remove this S or pre-subtract by using this extended constellation idea, the rate of user 1 can be expressed as if the user 2 is not there, right? But now since x2 was already designed, well, or let's say the power of x2 was already defined or already given, okay? And now x1 appears as independent Gaussian noise to user 2. If we look at the received signal at user 2, h2, x2 is the desired part, h2, x1 plus the noise. This is the interference plus noise. But since we assume this encoding order, that this is encoded first, this is encoded second, so it can be removed. Then this x1 is seen as interference for the user 2. Okay, and we get this desired signal divided by the interference plus noise. Okay, so just as a reminder, we can use also superposition coding and successive interference cancellation for this approach. This is something that we already discussed yesterday, right? In the superposition coding, right, this is the superposition still, we are designing the rate, again, exactly like here, designing the rate of user 2, assuming that user 1 has interference, right? And since user 1, because the channel channel gain is larger, its achievable rate is higher for given this x1, so it can also decode x1 and subtract, right? And it gets the same interference-free rate, right? So for this ordering, h1, h2, the same rate pair can be achieved also with superposition coding and successive interference cancellation at the receiver. But this requires now implementation of the SIC receiver at the user end, right? So it makes the user more complicated. And it only works for the given ordering, right? The ordering has to be exact. If we now switch the order, h2 is larger than h1, this rate pair does not work, right? Because the channel of user 1 would be weaker than user 2. So then, therefore, user 1 would not be able to decode the message intended to user 2, given the interference of user 1, because the channel would be smaller. Right? You can do that. Just plug in some values H1 and H2, and you will see that.
Even with the DPC?
But with DPC, the DPC can handle this, right? Because the interference is given, and we just pick a point from the extended constellation.
So in DPC, users even
User order, it doesn't matter.
Users are even don't understand what is happening, right? They just decode their message.
Yeah, but they need to know this extended alphabet, right?
But if I see, I mean, some intuitive from the previous extended figures, let's say we have for QPSK, we had the 16 constellations, right? From that, we can decode without knowing the other user data also. Right?
Yes, it's just a new origo.
Yes.
Right? The other user data sets the new origo, and it's actually the user does not know about the origo,
yes.
right? Because it just see the summation of these two vectors, right? So it just simply choose the points which is closest to the received noisy sample, right?
Okay. The reference has to be known. Constellation.
Well, there has to be some scale, like just like in practice, you have to have AGCs and whatsoever in place.
You should know what that sample means.
Yeah. Okay, we are not going into that level of practical details. Just to give you the basic idea. Just choose the point, assuming that everything can be handled using necessary practical steps. That's the difference, right? So SPC SIG can handle, in this scalar case, recall that the SPC SIG does not extend to the vector case because the ordering also depends on the beamformer, right? But now, since the DPC is the ordering is not required, so it can handle any scenario. That's why it can be plugged into this multi-antenna case. The ordering is not important, right? I mean, we have to know, of course, the encoding order, but any encoding order can be handled by DPC, unlike in the SPC. Okay. Okay, let's move on to the interesting part. Let's first cover the dual uplink. Okay. Let's assume that we have 3 users. Okay. 1, 2, 3, and corresponding channels. Okay, downlink channels, but let's consider now the dual uplink that we already discussed earlier for the linear case. Right, the dual uplink model for this is that, okay, that the user 1 is transmitting in dual uplink with Q1, or power Q1, or power Q2, Q3. So, and then we are interested in decoding a certain message, right? The user 1, the X of user 1 is Q1 D1, right? The power allocation at the symbol. All right, so the received signal in the dual uplink consists of the desired signal, okay, at the output of the received beamformer, UK Hermes and HK XK. XK is now Q square root defined over there, right? And then we have these 2 interference parts, right? I smaller than K, I larger than K, and I smaller than K, right? Now we are in the decode, we are in the dual uplink, so we can assume MMS is SIG, okay? So assuming a decoding order 1 to K, so capital K is decoded to last, meaning without interference, right? the first user is decoded with all the interference, right? If we choose user 1 to be decoded first, user 2 and 3 are still has interference, right? I think if we choose to decode user 2, user 1 appears here. Since it was decoded first, it can be subtracted, right? So this term here can be subtracted by using MMSE sig, or just sig at the moment, assuming U is fixed. Okay. Right, so the process, if we start from user 1, okay, this would be the desired signal. This is the interference. Well, choose U to be MMSE receiver, assuming 2 and 3 are interference. Decode D1, right? Assuming interference from users 2 and 3. Now, since D1 is already decoded, it can be subtracted from the received signal. So we can subtract HK Q1 D1, right? So from the user 2 perspective, user 1 is not there anymore. Okay, the interference is from user 3. Right? That's the MMSE sig structure. Okay. So if we now look at the SINR, given this decoding order from 1 to capital K, if you look at user 1, right, so we have Q1, H1 Hermitian U1 divided by M0, the noise, plus interference from users 2 and 3, right? For user 2, interference is from user 3. For user 3, no interference, right? Because users 1 and 2 are already removed. Right? This is the MMSE sig structure. Okay. So what happens? So we have still again the same expressions, but the inequality is replaced with the non-equality that we had earlier for the SINR formula is replaced by inequality, right? So some of these G terms are now missing altogether, right? The G, these are the G matrix terms, okay? If you look at the slide, slide 6, in equation 4.9, you have the SINR formula. There, the SINR formula, of course, contains interference from all other users except K, right? And this is with the linear processing, right? Not using successive interference cancelers. And then we, after doing the steps, we get this formula that includes all the SINR expressions, okay? 4.11 includes all the SINR expressions. Now, the SINR terms are missing some terms. So if we write SINR constraints or SINR expressions for these 3 users, what we get is this type of scenario: 1 minus B1, B2, B3 times what do we have here? So for the first user is in the first column of G. So we have G11, G21, G31. So we have interference from all other users, right? Q1, Q2, Q3. equals B1, B2, B2, B3 times N0. Right? So this first row here corresponds to the first user times the powers we get B1 times N0, right? Which is equivalent to the SINR expression, right? Just doing the multiplying the left-hand side with the denominator, adding the missing term, you get this expression. Just rearranging the SINR form. Okay. So for the second user, okay, user 2. Now the interference from user 1 is removed. So here we have 0. Okay. Then we have G22 and G3 2. Okay. For the third, there's no interference from user 1, neither from user 2. So we have just the own term, G33. Okay. So now we have a upper triangle matrix of this original G transpose matrix, right? Recall that G matrix has these indices reversed. Okay. So this is the G transpose. You can call this U upper triangular matrix of G transpose. So just like in the linear case, we can express the SINRs, assuming MMSC SIC structure, as a single matrix formula, where some of these terms from the G matrix are removed. That's a zeroed out, right? Make sense? Now this is the MMSC SIC structure for the dual uplink or uplink in general, right? But we are interested in how we can use this for the downlink case. Okay, obviously for the MMSC SIC, you have this flow of actions that, okay, first you have the MMSC receiver front end, decode, subtract, update the MMSC for the second user, decode, subtract, MMSC for the third user without interference from the previous steps, right? You can see that the MMSC receiver, well, actually the real MMSC receiver should also include the equality here, right? But both are equal from the SINR perspective. Whether the own term is here or not, it's the same. You can show the equivalence using the matrix inversion lemma, just like in your homework, right? So it extends to this MMSC SIC receiver, the linear front end of the MMSC SIC receiver. From the SINR perspective, these two versions of beamformers are exactly the same. This is the max SINR receiver, which is the scaled version of the MMSC. Here, in fact, I think they are the same. They should be the same. If they're normalized, actually, that becomes the same. Yes. So it doesn't matter whether you include. Well, you can check with MATLAB if you don't believe it. All right, so this is the MMSC receiver that you should apply at each step. Okay. So now, just a reminder before we have a break. If we have now this gamma expression, gamma uplink SIC which is QK HK permission UK divided by N0 plus some I, assuming decoding order 1 to K, right? So I larger than K, the interference only on users with higher index, right? QI HI permission UK. Sorry. UK. Okay. So now when you plug in here and here the optimal UK from there, what do you get? You get SINI expression that depends on the U. What would be the SINI expression? That would be HK. What do we have here in the interference? What do we have here? What are the indices here? Oh, larger than K. HI, QI. Okay. This is the SINI expression for each user. Now, when we plug in the SINR expression, let's do it for 2 users, just for simplicity. All right, so we have a sum of, say, K1, 2, block 1 plus gamma K uplink stick. Okay. Which is equivalent to user 1 is decoded first, so we have block 2 1 plus, what would be the user 1 SINR? H1. What do we have here? H2, Q2 plus N0I times H1 plus log 2 of what? 1 plus N2, H2, Q2 over N0. Okay. So how do we end up here? So now we can use the rule log 1 plus row vector times column vector equals log det I plus CR, right? And we can plug this rule in both, okay? So applying this one in here, what we in fact get is, okay, this becomes determinant, this becomes identity. This one moves here, right? So we have H1 permission here, this becomes determinant. Okay. Reverse. And similarly here, determinant, identity matrix. Okay. Right. Now, what you can do is that you have a log, sum of logs, log of products. Okay. So you have the determinant product of determinants inside the log. You have product of determinants is a determinant of products of two square matrices. And then this one actually, when you multiply with this matrix from the left, you get log 2 I plus Q1 N0 H1 permission plus Q2 N0 H2 permission, right? And then if you define Q to be diagonal matrix of Q1 and Q2 and stack H1 and H2 to matrix H, you get, okay. All right, let's take 5-minute break and continue, or we can use this for the download. Tell me when you're ready. It's recording?
Yes.
Okay.
Yes. Yes.
All right. Before we start and continue, there was a mistake in the exercise setup related to exercise number 2.
3. To assign question 3.
One second.
Question 3 assign homework 2.
Question 3 of homework 2. Okay. So about this greedy selection, so it's missing inverse, so it should be x I minus x times
X Hermes.
x Hermitian x inverse times x Hermitian, or other way around, as long as it's invertible, right? You can that description will be updated as soon as possible. If you use that expression, it's the same as that. Okay. All right, so we covered the dual uplink, the SI and I expression. Now, let's switch back to the original downlink, okay? And rewrite the received signal from a user K perspective. Okay, if you think about user 2, which is in the middle, now here we assume that the encoding order is reversed with respect to the uplink. Okay, this is important. Just assume, it becomes more clear later on, but assume now that encoding order is K to 1. So the user capital K is encoded first. Right, so there's no S for user capital K. It's a whiteboard, right? There's no writing, right, on the paper yet. Okay. So from the user K perspective, we have the desired signal, and then we have split the interference into 2 parts, right? Assuming this encoding order from K to 1, these indices I that are larger than K can be assumed as side information because those are already designed. This is the S vector, right? Okay. For user 3 here, there's no side information because we start encoding from user 3. Okay. So finally, the interference will be caused by both 1 and 2 at the receiver. Right? So think about user 2. That we have user 2 here, the desired signal. So if you think about SI and R, P2 times H2 Hermitian times U2. Okay. Assuming dirty paper coding strategy, for user 2, we can treat the signal vector is now in vector domain because it also contains the beamformer U. Signal vector that was designed for user 3 as something that we can take as a side information, right? This is the S. So we can now choose a point from the extended constellation, assuming the user 3 has shifted the origo, right? Okay. So user 3 for user 2 is side information, known as a transmit. Okay, and that can be pre-subtracted using this dirty paper coding idea. Right? The user 1 is seen as additive Gaussian noise because it's encoded after user 2. Okay. Finally, user 1 is encoded after user 1 and 2, so the superposition of 1 and 2 is seen as side information available as a transmitter. Right, so this is the new origo. Superposition of user 1 and 2 is the new origo for the user 2, for user 1, and then applying the dirty paper coding idea, user 1 will see no interference. Okay, so we can now express the downlink dirty paper coding SINR such that given this encoding order, right? This only applies for this encoding order. That we have the desired signal, noise, and interference from user indices that are smaller than K. Okay. If the encoding order is other way around, then the interference would be from user indices larger than K. Okay. Is it clear? It just depends on the encoding order. Encoding order, when you start from whatever user, you can have you can quite often, this is expressed as, let's say, pi gives a whatever arbitrary arrangement of user indices, right? Could be 3, 2, let's say 3, 1, 2, right? Or 1, 3, 2, or whatever. For 3 users, there's 6 possible combinations. Okay. And then this order is then, you just pi defines the order of indices, and then if you use this notation, kth index of order pi, right? So you can just apply, you can replace this strict indexing with, let's say, relative indexing, right? It's the kth index of arbitrary index vector, right? And this is actually something that we will be using. So now, assuming the dirty paper coding, when you now draw the SINR matrix, gather all the system of equations, right? We have 3 equations for 3 users. We can do the same steps as earlier. We can express for this 3 user case. Let's say we have 1, 1, 1, 0, 0, 0, minus A1, A2, A3. Okay, then we have the G matrix or the coupling matrix. And then we have the P1, P2, P3 equals A1, A2, A3 times n0. Okay, let's start looking. What do we have there in the G matrix or partial G matrix? It's clear that some of those G's are zeros, right? Because they are removed, pre-subtracted. So, assuming encoding order 1 to K, the first user, K to 1. The user 1 is then encoded with full information of others, so it can be removed. So we have G1, 1, and then 0 and 0, right? No interference from users 2 and 3. For user 2, this is the decide part, we have interference from user 1, but nothing from user 3. Yes. Let me see. Yes, with encoding order 3, 2, 1, right? Encoding order 3, 2, 1. Okay. And from the user 3 perspective, since it's encoded first, interference from both. Okay. Now we have lower triangular of G matrix. Okay. It's given here. And obviously, it's the same as upper of G transpose, right? So this is something which we will utilize later on, when we again now go back to this sum power argument. Okay, you can see that the lower triangle of G matrix is the same as upper triangle of G transpose. Okay, this is what we have seen from these two examples. Okay, now if we assign the same set of SIMRs for both downlink and dual uplink, let's say 10 dB for every user, meaning that again A equals B and the DA equals DB. SIMR is the same. Now, for this given set of SINRs and beamformers, okay, let's get back to the beamformer later on. Let's assume the beamformers are given. We can write again the sum power, are doing the same steps as earlier. So this is the P expression, right? The P vector is the downlink power. We can do exactly the same steps as for the linear case. We get this equivalent expression for the power P vector that includes P1, P2, P3. Okay. And this operation is the sum of powers. Now we can use the same tricks as again, that we can include here a transpose without any loss. It's the same sum. If we add here, if we are summing up all the entries of this matrix, include transpose, doesn't change anything, and then we use the same rule as before, that the transpose of inverse is the same as inverse of transpose. Okay, and we get this one, and let me see. And then we just transpose the lower triangular matrix of G. It becomes, let me see. It becomes the G transpose, upper triangular of G transpose. Okay, and then this is the equivalent to the Q vector, right? Sum Q. So by using this equivalence, you can show that for a given set of fixed SINR constraints, the same beamformers, both uplink and same normalized beamformers, uplink and downlink, you can find a power allocation or given uplink power allocation, you can find a different downlink power allocation that achieves the same SINRs or vice versa. Okay, the power allocation is different, right? This interference structure is different as well, right? The indices are different, but the sum power is the same. The power allocation is different. So, in other words, there exists a downlink power P with this constraint, the sum power is the same, such that this holds. So now, since we have this, so this is the downlink DPC SINR, but we can achieve the same SINR in the uplink. So we just replace this with the uplink NMSC to get this expression, just like in the dual uplink, right? But now we have a power constraint, which is the total power constraint for P, which is total constraint for Q. Okay, so it means that the transmit power constraint, which is trace of X permission, is the downlink, the same as trace of covariance matrix yeah, this is the same as covariance matrix, trace of covariance matrix. This is the same as summing user-specific covariance matrices. This is the same as user-specific power, sum power, same as sum power in uplink, right? And this is now constrained by P, just one power constraint. So we can maximize this sum, right? We can maximize this sum of rates in the dual uplink, for which we can also find corresponding SINRs in the downlink after conversion by simply summing this form, this expression here, subject to some power constraint. Okay. This is a convex problem, right? We have a concave objective and linear constraints, or set of linear constraints. But of course, the power should be positive. So this we can solve. If we try to solve this one directly in the downlink, it's impossible. If we write here the SINR expressions for the downlink, it's neither concave nor convex. We cannot rearrange it in the same as in the uplink case. That would be sum of concave functions in the weighted sum rate. Well, just one concave function in the sum rate case. So the downlink we cannot solve directly, but we can solve the dual uplink based on which we can find a optimal downlink scheme. Well, we haven't proven here the optimality. The deep is that the first steps, for example, with these guys, they came up with the idea of using DPC because of this duality. And then they first saw that, okay, it's sum rate optimal using this Sato bound and other arguments, I don't remember. So first they like around before that, people didn't talk about broadcast rate region, some capacity of broadcast channel, but capacity of the DPC, right? This was not yet proven that this is actually the optimal strategy, but that was also proven later on. Like this guy talks about sum capacity of the vector, only the sum capacity. Sum rate, right? First they only were able to show the sum rate optimally. Also sum capacity, only this guy there to mention capacity region. All right, interesting fact is that if we think about point to point, think about this, for example, this would be 3 by 3 MIMO, point to point MIMO, full cooperation. Interesting thing is that the C sum given here is equal to the capacity of, let's say, 3 by 3 point to point MIMO channel with the least favorable noise. Right? So assuming that we have a point to point, and then the noise vector that we add at the receiver follows complex Gaussian 0 with covariance matrix Z instead of N0I, which would be the real point to point. You can show that if you add this Z as a variable into the rate maximization, this we discussed also earlier, point-to-point MIMO with interference, how to handle widening of Z, right? But now Z is variable here. So you have two variables, Kx and Z. So you can define for fixed Z is a point-to-point capacity. With Z you can optimize this with just simple widening and SVD. Right, for fixed Z, find the Kx. But then we have also, we should find the worst possible Z that minimizes this. So we have a max-min problem. It's somewhat complicated to solve, but it's solvable. One heuristic solution is to alternate between these two. It's not guaranteed to converge, but quite often converges to the optimum, but it's not guaranteed. Because Z actually, this is a convex function with respect to Z, concave function with respect to K. So you can alternate, maximizing, minimizing, maximizing, minimizing. But anyways, it's just nice to know. You can, well, you won't need that knowledge to pass this course. So you may very well forget that. Okay, what about the rate region? So now we have to rate some rate. By the way, let me just write down the steps before we get here. The question is that how, okay, we know that, okay, this is the dual, sum rate of the dual uplink. How do we recover the downlink strategy? Okay, let me write, this might be actually a question in the exam. So think about it. So let's see, we have a problem to maximize the capacity of the downlink channel, right? So we have a downlink DPC. Subject to power constraints. Let's say just to make things simple, let's define a new variable mk, which is the downlink beamformer, including the power. So uk times pk. Recall uk is the normalized beamformer, pk is the power, right? So uk times pk equals mk, meaning that the norm of mk is pk, right? Two more, sorry. All right, so we can express that as right? This would be the optimization problem. Maximize the downlink rate subject to power constraints. Okay. This MK you can express. Now the SINR would be would be HK Hermitian times MK, and PK would be included in the UK, right? It's equivalent. Now, if you want to plug these SINR expressions here, no way you can solve it optimally. You can start doing all kind of relaxations and stuff like that to get local solution, but optimally it is not guaranteed. So the steps to solve this: the first step, convert to dual uplink. Okay. Then solve uh, 438. Okay. After solving 438, you get the optimal powers Q. Okay. Now you should decide the encoding and decoding order, right? For the sum rate, you can do anything, right? But later on, for the rate region, you should take into account the priority, right? The priority defines the encoding. The highest priority user should be encoded first or decoded last, right? And decoded last in the dual uplink. The lowest priority user should be decoded first, meaning encoded last. Yeah. Decoded first, encoded last, yes. All right. So now you have decided a certain decoding and reverse encoding order. But this has to be always reversed for this duality to hold. That's a must. Encoding order is reverse decoding order, and vice versa. Okay, for any for a given reverse encoding order, compute, let's say for reverse encoding order, compute UK, the receivers, the dual uplink receivers, which are given in 431. Right. You can see that 431 depends only on this Q that you have already optimized. Okay, but now you have to have this correct decoding order, which is reversed encoding order. Right. If the encoding order is 1 to K, decoding order is K to 1. All right. Now you have the UK, you have the QK. You can compute the SIN. Step 4. Compute gamma K uplink. And that's given in the 429. Okay. Now you have the SINR fixed, U fixed. Okay. You can solve P in the original. In the downlink, right? dA is now given, dA plus dB. The SIN for the same set of SINRs in dual uplink is also achievable in the original downlink, right? Using these beamformers. And this G matrix is because beamformers are computed U, so you can compute the G matrix. right? So everything is known here except P, but you can solve P just by inverting this one, right? So solve P. So P from 4, 3, 4. What is left? Compute the beamformers, right? MK equals UK VK square root. So now we have the downlink beamformers. Those are the steps. So obviously here, later on when we discuss about the rate region, the encoding order, right? You recall that when you have the rate region, when you have some rate, it's the 2-user case, right? When you are in this region, user 1 should be decoded last, right? Here, user 2 should be decoded last, right? So the priority, so user 1 has higher priority here, so it's decoded last, but it's encoded first, right? Just hopefully it will become more clear why this reverse. Well, the reverse is required for the duality to hold, right? If we use the same encoding order and decoding order, it doesn't hold, right? We cannot do this. We cannot find a power allocation that would satisfy the SINR. All right. Okay, rate region. So now here I introduce this pi vector. Pi is now any arbitrary ordering of indices, right? If you have 10 users, then you have choose 10 combinations, right? Any combination, but then you should just fix the encoding order depending on your priority, right? If you choose that user 5 has the highest priority, it should be encoded first, decoded last, right? Okay, in general, we're interested in the rate expression in the downlink of user K. Okay, so we have a usual. So now we have the downlink case. Let's say we are interested in, given the interference from users 1 and 3, with one of them can be removed by DBC. What would be the rate of user 2? So we can ask again usual information between XK and YK given. So we can remove something given. So in the encoding order 1 to capital K. Given x1 to xk minus 1. Okay, these users with smaller indices can be removed, right? Because for user k, this is already prior info. They have been already encoded. Superposition of all this is the new origo, right? So now we just plug in here. We have H, entropy of H, entropy of Y, K, given x1 to x k minus 1 minus what? entropy yk. Well, you can think this. But it's a difficult, it's a k-dimensional problem. But you have to add, you have to also remove k, right? x1, xk. Okay. So now you have the variance. This is a scalar. So variance of yk given x1 minus xk. This is the rate. It's log ie variance of that, which would be n0 plus some I larger or equal to k hi remission sorry, transmit covariance matrix. So maybe that requires one step. Where the kx come from? So yk, say hk, xk, xk you can think as that. What's the downlink? Sorry. Xk is uk, ek, vk. This is the transmitted vector for user k. And then we have all the intercepts, xk, I larger than k. Right. Okay, this is the signal model. And now you can define that this is transmitted signal vector of xk. So xk is a Gaussian distributed zero mean with covariance kxk, right? In the end, of course, it's a rank 1 matrix. So kx, k is uk remission pk, right? But in general, kxk. Okay, so now in this, when we plug in here, we just consider this transmit covariance matrix. Okay, so this is the differential entropy of this term minus differential entropy of the other term, which is n0 plus some I larger than k. And the same, hi, kx, I, hi. Right? So it's this one here, right? It's a difference of log, so log of ratio. This one here corresponds to the first term, and this is the second term. And then we can just divide them. You get 1 plus the SI line. This is the SI line, the down, right? Kx, if we plug in here, this expression UK Hermison PK, you get exactly the same SI and I expression for the downlink as earlier for this given encoding order. It actually now looks different because we have a different encoding order as in the earlier slide, right? All right, so now we have these rate expressions. So the rate region defined as the convex hull of the union of all feasible rate allocations for all possible orderings. Right. This is for a given order, a given transmit covariance matrix. Now, in principle, if you want to cover without doing this blindly for the downlink, we could have an exhaustive search over all possible encoding orders, and for each fixed encoding order, all possible feasible power allocation. This is the feasibility. So transmit power constraints. So over all feasible power allocations over all permutations. Of course, it's impossible. It's infinite number of combinations. Cannot be handled. But that holds in principle. So we have the broadcast region is the convex hull over all possible permutations and feasible power allocations, collecting those rate pairs, or rate pair for 2 users, but rate vectors for users. So region is difficult, neither convex nor concave, and you have all these combinations. So we cannot solve this in downlink directly. Now, just going one step back, we have the MAC capacity. If we have a fixed powers in uplink, these are our uplink powers. The rate region is given by this multi-hedra, whatever it's, polyhedra. Pentagon for two users, this igloo for 3 users, and so forth. Okay, so for all possible subsets of these k users, we have this sum rate constraints. 3 users we have 2 users we have 3 constraints. 3 users we have 7 constraints, and so forth. So you can also show that the broadcast capacity with this sum power constraint is equal to union of all possible multi-access channel capacity for fixed power constraints. It's already much easier, right? You have multi-access. This is a 1 pentagon for a given power allocation. Now you just try all possible power allocations and take a union, right? So you can actually, it has been shown in one of those references that the last one, that this union corresponds to the actual rate region of the broadcast. And you can solve this. And this is actually your homework. It's one of, you can relax for the multi-antenna case. Instead of having per antenna power constraints, per user power constraints, you have the sum power constraint. You can solve the weighted sum rate maximization given the sum power constraint. So when you plot that, that's actually the capacity region for the downlink with some power constraint, right? So that's the side product of your uplink homework. Okay. So now you have also an algorithm to find also the downlink broadcast capacity region. Just replacing the individual power constraints with total power constraints. All right. So this is actually the simplest possible case. When we have 2 users, you don't have to even solve anything because going through all the combinations or with fine enough grid is doable. Here, let's say we have 2 users, so P1 plus P2 equals Q1 plus Q2 is capital P. I think it's 1 in this particular case, I think, looking at the numbers. So what you need to do is just to make a grid, like here is 100 realizations of all these ratios, right? That generate a vector of Q1s and Q2s such that Q1 plus Q2 equals 1. Okay, easy to do. And now what you do is that for each pair Q1 and Q2 for fixed channels, you generate a pentagon, right? And then you just plot those pentagons on top of each other, and this is what you get. Here we have allocated, the first point here, we have allocated most of the power to user 1, right? And these are the 2 points with different decoding orders, given Q1, given fixed Q1, Q2, okay? Now we start gradually adding more power to user 2, right? In the other end, we have allocated almost all the powers for user 2. And of course, we can allocate all the power to user 2, and we get this one more extra point here and here, right? Just doing match filter transmission. And this is your rate region. When you connect those dots, that's the rate region for the 2 user case. Okay. But going beyond 2 users, you can imagine it grows cubic. It's for the 3 user case, you would need to maintain the same granularity, you would need 100 by 100, 10,000 points, right? So it grows exponentially, the complexity for single antenna. Now, if you have multi-antenna case, impossible, because it becomes a vector, right? Complex valued vector optimization. Okay, but this you can solve using your, hopefully that you have already implemented your algorithm, replacing the transmit covariance matrix with a single antenna. Okay, Q, instead of optimizing KXK, you optimize QK. Okay, transmit covariance matrix collapses to power when you have a single antenna at the users. Okay, you can generate this using weighted sum rate maximizers. Okay, time is up. So the multi-antenna extension, it's very straightforward, but it's excluded from the first midterm because I don't have time to cover it. So first midterm will include everything up to this slide, okay? And the homeworks. Just a couple of slides left. Okay.
So greedy selection, we have made some mistake. Please check the new update.
Yes, the updated homework description will be.
It is available now.
It's already available. Okay, good.
Do we have session tomorrow or that for tomorrow?
So tomorrow is the homework exercise.
We can have
session.
also on Monday.
Friday, Monday.
Is it? Okay.
Friday we can have.
Friday we can have.
If you guys have any trouble, otherwise we can have tomorrow.
Friday better.
All right. Okay. Anyways, communicate that so we can extend the homework by 1 day to Friday to give you more time. Also, given this mistake in the definition.
The exercise session on Friday.
What was that?
The exercise session will be on Friday.
Yeah,
Yes.
if you want. Otherwise,
If you want, if you have accept, of course, we will post the video then if you are not able to attend. Okay, but you have time, 1 more day, extra time to return the second exercise, okay? And Tuesday, 9:15, or maybe earlier, we will start the exam in PR something. All right, and let me know, whoever wants to take the exam online, send me an email so I can prepare in advance. Okay, a couple of guys have already contacted, but yeah. All right, others should be there in person. See you on Tuesday.